Welcome to IISc MSR Theory Seminar Series. Today's speaker is a student at IISc itself, Rishikesh Gajjala. He is a second-year PhD student in theoretical computer science and works with Professor Sunil Chandran on combinatorial problems in different fields. Prior to this, he completed his bachelor's in computer science at IIT Delhi. In the past, he has worked on causal inference and data compression algorithms and has published in places like AI Stats and FST-TCS. And his recent work, his latest work with Professor Chandran, won the on Krenn's conjecture, won the €1,000 Best Paper Award, the prize for which is sponsoring today's lunch. So naturally, today's talk is on their work on progress in Krenn's conjecture, which is about perfect matchings in quantum physics. So please welcome Rishikesh.
Thanks for the introduction, Atisi. So today's talk will be on perfect matchings and quantum physics. Yeah, it's on. Am I audible? So before starting the talk, there'll be a lot of definitions in the talk which will be new. So if you forget a definition or anything, please feel free to stop and ask what it is, or if you have any questions. And this is a question formulated by quantum physicists in graph-theoretic terms. So initially, I'll be giving an intuition of how this problem translates into graph-theoretic language. Then we'll solve this graph-theoretic problem and then translate it back to quantum physics. So for the transition from quantum physics to perfect matchings, I'll only be giving some intuition. So quantum entanglement says that two particles can influence each other, even though they're separated over large distances. This is in some sense counterintuitive and one of the most mind-boggling phenomenon predicted by quantum physics. Einstein called it spooky action at a distance. This is for two particles. A further, more spookier thing you could say is when the state is extended to more than 2 qubits. That is, there are multiple qubits which are entangled with each other. So the question we are interested in is generating GZ states which have large dimension. The entanglement shared among several parties is used in communication protocols and cryptographic applications. So huge effort is, because of these applications, huge effort is being made by several experimental groups around the world to push the size of GZ states. And photonic technology is one of the main players in this game. So the main question we'll be focusing on rest of the talk is, can high-dimensional GZ states be created in some particular quantum optical setup? We'll first see what this setup is and how this experimental setup translates to a graph. So on the left, you have the experimental setup. On the right is the graph corresponding to it. So if you take an undirected, uncolored graph, that graph would correspond to a quantum optical experiment. We'll understand what it is by looking at what vertices mean, what edges mean, and so on in a while. So in So in the figure A, B, C, D are the photon detectors, and 1, 2, 3, 4 are crystals where photons are starting, and these paths are the optical paths. In each crystal, there is a photon pair which is being started, and these should be detected by the photon detectors A, B, C, D. These photon detectors A, B, C, D correspond to the vertices A, B, C, D in this graph. And we know that each of this crystal corresponds to a photon pair, and this pair corresponds to an edge in this graph. So if you see these two green crystals, 1 and 2, they correspond to the edges 1 and 2 in this. And two blue edges 3 and 4 correspond to the edges AC and BD. And if you see the paths starting from, let's say, the crystal 3, the first photon can be detected by the photon detector A, and the second photon in the pair, which is being started in 3, can be detected by the photon detector C. Therefore, the edge 3 is between the vertex A and C. Similarly, if you pick the vertex 2, one photon path goes to C, other path goes to B. Therefore, the crystal 2 is the edge 2 here, which is between the vertices B and C. Now we are interested in the event in the experiment where A, B, C, D, all of them detect a photon at a time. And these photon pairs are entangled. So 2 pairs must be, it shouldn't be the case that 1 pair is detected and other pair is not detected. Every time, either both the pairs get detected or they won't. So we are interested in the event where all photon pairs detect a photon. So in particular, we want 4 photons to be detected from these crystals, and that should happen in pairs. So it should be the case that 2 of these crystals should give photons, 2 each, so that the pairs ABCD the photon detectors ABCD detect a photon. Now, one example is you can pick one here. One has a photon to A and a photon to D, and 2 has a photon to C and photon to B. So if you pick the crystals 1 and 2, they together can make will correspond to an event where all photons are ABCD all detect a photon. So now we can see that in graph theoretic language, these are the vertices which needs to be covered using some crystals. So we need edges which are disjoint, which can cover all the vertices. That is nothing but a perfect matching. Therefore, looking at these multi-photon events where each single photon detector detects a photon is nothing but a perfect matching in this graph. Can you be loud? Yeah. So we're interested in the event where the photon detectors A, B, C, D, all of them detect a photon. And each of these photons can be detected only in pairs. So since there are 4 photon detectors, and you need pairs to be detected, so you can select 2 pairs. So these 2 pairs should start from 2 crystals. Let's say that starting from 1 and 2, then 1 covers A and D, 2 covers C and B. So this is done. Let's say if we pick 1 and 4, then 1 covers A and D, but 4 again covers B and D. C is not covered. So this is not in, and B detects 2 things. That is also not covered. You want a disjoint union, which covers all these A, B, C, D. So a perfect matching is exactly that. So now we'll see what edge colors and edge weights are in this graph. So edge colors correspond to the mode number of photons in the path. What mode number is not really required for us. We know that it's a parameter which the experimentalist can set. So in each crystal, we are seeing that it's singly colored. Let's say if you take the crystal 1, in that it's green colored and both photons correspond to green color. But it could be the case that you could create the crystal in such a way that this photon gets the color green and this photon gets the color blue. So each crystal can have 2 colors. That's by giving 2 mode numbers to both the photons. So these graph can be a bicolored graph. Let's say if I do that for crystal 1, the first part of 1 will be blue and the second part of 1 will be red. And the edge weights correspond, each of these photon pairs in these crystals will have an amplitude corresponding to them, and the edge weight corresponds to that amplitude. So both these parameters, the mode number and the amplitude of the photon pair, they can be set by the experimenter. So given a graph, we have complete control over what the colors can be and the weights can be. And we want to pick these colors and weights in such a way that certain properties are satisfied by this graph. Because then once we do that, we'll just give back the amplitude, that is weights, and the colors, which is mode number, to the experimenter, and they can set it in the experiment such that we'll get a GSZ state of some high dimension. So now we are only interested to see what those certain properties are and how to vary the colors and weight so that certain properties are satisfied. Okay, let's look at this graph. This is a bicolored graph, as I said earlier. Each edge can get two colors. One correspond to the first part of the vertex and second correspond to the other part of the vertex. And all of these four vertices have weight 1, and the two horizontal edges have weight I. Sorry, these four edges have weight +1. Now this graph has three perfect matchings. One is the cross pair, other is the vertical pair, and other is the horizontal pair. Now if you take the cross pair, this pair corresponds to the quantum event where the photon detectors 1, 2, 3, 4, that is the vertices 1, 2, 3, 4, all of them detect, let's say green correspond to some number x number of mode photons at a time. So whenever we take this perfect matching, all these vertices correspond to color green, and in the experiment, all the photon detectors correspond to the mode number corresponding to green. Now, if you take these two colorings in this set of edges, both 1, 2 and 3, 4 have a perfect matching, and these have a different perfect matching. Now, we can see that in both these colorings, they correspond to the same event. That is, 1 and 4 get the color blue, so they detect the mode number of photons of corresponding to blue, and 2 and 3 correspond to the color red, and they detect the mode number of colors corresponding to red. Even in this graph, the same thing is happening. 2 and 3 gets the color red, 1 and 4 gets the color blue. So in this perfect matching. So both these perfect matchings correspond to the same quantum event. Therefore, we can just add them up. So we'll do this again. So we want to talk about some particular properties these weighted and colored graphs satisfy. So we'll get to that property now. All events in which
you have to tell what is the weight of the matching is.
Yeah, I'll tell that now. Okay. Now if we take the quantum event in which same number of mode photon pairs are detected, they should have weight 1. Now we'll see what the weight of such a state is. Consider this all green matching. In this, there is a +1 weight here and +1 weight here. And the weight of this matching is nothing but +1 into +1. That is multiplying all the amplitudes. Therefore, the weight of all G's, 1, 2, 3, 4 to be G, is nothing but 1 into 1. So all the other events in which the same mode number of photons are not detected. So in this, it was a mix of blue and red. Here it was all green. So all these events should have weight 0. But we saw that both these events correspond to the same event, because 1 and 4 get the color blue and 2 and 3 get the color red in both the events. So for such a coloring, we'll just add both these contributions. So the contribution of this would be +1 into +1. And the edge weights can be complex because these are amplitudes. So the weight corresponding to 2, 3, and 1, 4 would be I into I. Therefore, the total weight of this would be I into I plus 1 into 1. That is 1 minus 1, which is 0. So we want this property that all the... So we'll see what this property means in graph-theoretic terms. Now, we saw that each perfect matching is inducing a vertex coloring. So in this, since each edge covers only exactly one vertex in the perfect matching, whenever you pick a perfect matching, that gives the inherited vertex coloring to all the vertices. So consider a monochromatic inherited vertex coloring. For example, this one, in which all vertices get the color green. All the perfect matchings corresponding to this should add up to weight 1. And consider a non-monochromatic vertex coloring. In this, where 1, 4 is blue and 2, 3 is red. All these corresponding to, in this case, there is only one non-monochromatic inherited vertex coloring, but in general, a graph could have a lot of them. All those should add up to 0. So this is the property we are interested in, and we want to construct graphs with high dimension. I'll get to what dimension is. High dimension satisfying this particular property. And we can assign weights and colors to the graph so that this property is satisfied.
The meaning of this adding up.
Since these corresponding to the same event, they interfere each other and you just add them. So to get the total weight of, yeah. Is any part not clear? So edge weights, these are given for a, so we are saying whether a graph, colored weighted graph is being perfectly monochromatic or not. So these are the inputs. There is a graph, there are some colors and the weights. Now, if these are given, we want to check whether it's perfectly monochromatic or not. For this, the first step is we are picking all green vertex coloring. And for that, we are multiplying all the weights of the edges. So here the weights are +1 and +1. So we are taking the product of them, which is 1. And similarly, if there are multiple perfect matchings corresponding to the same vertex coloring, you take the product for each term and add them up. So the weight of this thing would be +1 into +1. And here the weights are I and I. Yeah, weight of the matching is the product of the edge weight. And weight of the vertex coloring corresponding to a matching is, there are multiple matchings. We sum up all those edge weights. So in this case, we had two matchings which correspond to the same vertex coloring, and we add both of them up. This is +1 and this is -1, and we are adding them up. And all such things should be 0 when it's non-monochromatic. And whenever it's monochromatic, all such things should go to 8-1. I'll give one more example. So they corresponding to the same event, and I'm not sure, like they had. Yeah, they interfere and their weight should add up, which correspond to. Yeah, they can. I'll get to that. Destructive or.
So I can maybe I missed this. But every vertex does not have a fixed color. I mean.
Yeah, initially we don't give any colors to the vertex. We pick the perfect matchings, and each vertex.
Why don't you summarize? So just what is required.
Yeah.
I don't want you to derail that. I just want to clarify that. Look at vertex 2, for example.
Yeah.
It has two red outgoing half edges.
Yeah.
But only one green.
Yes.
So this is prescribed.
This is given. And once this is given, we'll see individual perfect matchings. Yeah.
Half edges, right?
Yeah, they're half edges. They can be full. So now let's see what a one-dimensional Z-Z state is. If you see the following graph, in this there are 3 perfect matchings. The horizontal pair, vertical pair, and the cross pair. And each of this edge has weight 1/√3. So if you take the horizontal perfect matching, its weight is 1/√3 into 1/√3. So it's 1/3. And the cross pair is also 1/3. And the horizontal pair is also 1/3. And they correspond to the same vertex coloring in which all of them are red. Therefore, you just add them up and see that it's 1. And since everything is red, there are no non-monochromatic vertex coloring in this. So this is a perfectly monochromatic graph. And since there is one color, which is monochromatic, which has a monochromatic vertex coloring, which has weight 1, we say that this is a one-dimensional Z-Z state. So the weight of an event correspond to all the photon pairs amplitudes be multiplied. Therefore, this is a one-dimensional Z-Z state. Let's see what a two-dimensional Z-Z state looks like. Yes, and each not matchings, each vertex coloring, and a vertex coloring corresponds to multiple matchings. So in this case, there are 3 perfect matchings which correspond to the color all reds. Therefore, that should sum, all three together should sum up to 1. So if you take a two-dimensional ZZ, this is an example of a two-dimensional ZZ state. So there are 3 perfect matchings again. And all blue vertex coloring is possible. Only the perfect matching 1, 4, and 2, 3 are considered. So the weight is nothing but +1. And all red vertex coloring correspond to 1, 2, and 3, 4 picked, or 2, 4, and 1, 3 picked. And we are giving the weights 1/√2 to each of them. So they sum up to 1 as well. And there are no non-monochromatic vertex colorings in this case too. Yeah, when the event where all photon detectors detect the same mode number. So now I'll give an example where in both these cases we just discussed, there were no non-monochromatic vertex colorings. I'll give one more example where there is a non-monochromatic vertex coloring. So in this case, so I'll define that properly later. So here there is only one color, which is a color for which there is a monochromatic vertex coloring, which will add up to 1. So in the second case, the colors both blue and red have monochromatic vertex colorings, which add up to 1. Therefore, we call it a two-dimensional ZZ state because there are 2 final states which are being created of weight 1, and they're equally likely, and that's why it's a two-dimensional ZZ state. So here is another. So earlier, both the examples, it was just the number of colors. Here is a one-dimensional ZZ state. So, but there are 3 colors. We'll see why. So in this, there are 2 inherited vertex colorings. First is all green, and that weight corresponds to +1 into +1. So that is clear. Now, there is a non-monochromatic vertex coloring here, in which 1, 4 get the color blue and 2, 3 get the color red. And there are 2 perfect matchings again, which correspond to this non-monochromatic vertex coloring. One has weight +1 and +1 with 1, 2, and 3, 4. And other has weight I and I, 1, 4, and 2, 3. And both of these add up to 0. Therefore, it's satisfying both the properties. And there is one monochromatic vertex coloring, which is green, which has weight 1. Therefore, this is a one-dimensional ZZ state. So let's take it further and see for the K4 itself, can we do 3 dimensions? So I'll just put different colors to all matchings. The cross matching gets green color, horizontal one gets red color, and vertical one gets blue color. And I'm giving weight +1 to everything. Therefore, all the monochromatic vertex colorings correspond to green, red, and blue have weight 1. So this has weighted matching index 3. Sorry, it has when we do this experiment, we'll end up getting a 3-dimensional ZZ state. So the question is, let's consider K4 only. Can we do better than 3 colors? We can't. Can someone guess why? So here we did it with 3 colors. Let's say I want to color these edges in such a way that I get a 4-dimensional state. Yeah. And number of edges is 6. And each perfect matching should have 2 edges. So you just divide 6 by 2, and the best you can achieve is 3. Now, another way to look at it is each perfect matching. Okay, there is another claim. If you take a K4 here, there is a relation between the degree and the dimension, the best dimension you can achieve. So pick the vertex 3. It has dimension 3. What happens if you want to create a ZZ state of dimension 4? Can you guess? Can you? Yeah. So if there are n perfect matchings, there should be at least n edges on that vertex. Since, let's say if the graph has minimum degree k, if there are k+1 perfect matchings, you'll get a contradiction. Therefore, one trivial bound for any graph is that the dimension of that graph, whatever colors and weights you give, can't exceed the minimum degree. Now we'll define something called matching index for an unweighted uncolored graph. So we saw that multiple possible colorings and weights were possible for K4, but out of all possible colorings and weights, the best dimension we could achieve was only 3. So we will extend this concept to any graph in general. Take any graph, consider the space with all colorings and all weights. Over all those things, when each of these colored weighted graphs are perfectly monochromatic, you have to pick the dimension the best dimension you can achieve. So for K4, we tried those colorings and we saw that the best we can achieve is 3, and we proved a case where 3 happens. Yeah, all weights can be complex because amplitudes can be complex. Now the question we are interested in the following: are there graphs with a high matching index? For K4, we created a graph with a 3-dimensional ZZ state. So if you find a graph with a high matching index, then you can find a coloring and weight with that particular matching index, and you can create a high-dimensional ZZ state. So that's how we create a high-dimensional ZZ. So far, no graphs other than K4 is known with matching index at least 3. So it's at least 3 because other than K4, graphs are not even known with a weighted matching index 3. Whatever is known has weighted matching index less than or equal to 2. And we'll use the notation mu bar to denote the weighted matching index of a graph. Now I'll go to a simpler case. When we are adding multiple perfect matchings corresponding to the same vertex coloring, they can, in the earlier case, one was weighing 1 and other was weighing -1, and they were interfering destructively. If we don't allow such a destructive interference, that is, all of them only add up to a higher value. This happens when all the edge weights are positive real valued also. We are interested in that case, and in that case, we'll say that the problem reduces to a simple case when all perfect matchings are monochromatic. So there can't be any non-monochromatic perfect matchings. We'll prove that now. Sure. So let's say there is a graph with a non-monochromatic perfect matching with all edge weights are positive. Then this graph, since there is a non-monochromatic perfect matching, there is a non-monochromatic vertex coloring associated to it too. And that non-monochromatic vertex coloring could have multiple perfect matchings which are non-chromatic associated with it. But we know that all these things have positive weight because the edge weights are positive in this in the case when there is no destructive interference. So all these sum up to some positive weight. But by definition, we know that non-monochromatic vertex colorings should have weight 0. But that's a contradiction. Therefore, we know that in these graphs, there is all the perfect matchings are monochromatic. Now, let's take such a graph which is unweighted. You have a graph in which all perfect matchings are monochromatic, and taking that graph, we want to assign weights in such a way that we are getting a perfectly monochromatic graph in the weighted sense. So let's consider this simple example. In this, there are 3 perfect matchings. 2 are red and 1 is blue. And so in this, there are no non-monochromatic perfect matchings. We want to assign weights to these edges such that it's perfectly monochromatic. That is, all monochromatic vertex colorings have weight 1. We don't have to worry about non-monochromatic vertex colorings because they don't exist in such graphs. So in this particular case, since there is only one blue matching, I can just give the weights 1 and 1 to both of them. Since there are 2 red perfect matchings, I'll make sure that one perfect matching contributes 1/2 and other perfect matching contributes 1/2. And once you know that both of them should be 1/2, I'll give edge weights 1/2 to both of them, so that when their product is taken, each of them sums up becomes 1/2. So let's see how we can extend it to a general coloring in which there is no perfectly monochromatic graph. You pick any color, see number of perfect matchings for the monochromatic vertex coloring of that color. You make sure that each of these perfect matchings has weight 1 by number of perfect matchings. And since there are n/2 edges, you'll just put power 2 by n for all of these so that they sum up to 1 by perfect matching and they'll add up to 1. So finally, if there is a graph satisfying this property that there are no monochromatic vertex colorings, you can also do the other way. you can create a perfectly monochromatic graph. So this case where there is no destructive interference is as good as considering the case of unweighted graphs where there are no monochromatic perfect matchings, no non-monochromatic perfect matchings. So for this particular setup, when all edge weights are restricted to be positive, we'll consider the maximum dimension achievable to be the unweighted matching index of the graph, and we'll denote by mu of g. We call that the earlier matching index we defined for the weighted case was mu bar of g.
So, very nice question.
Examples of that.
Where there is no, yeah, this is an example, right? In this, all weights are 1 by root 2, red weights, and blue weights are 1, and blue weights sum up to 1, red weights sum up to 1. Yeah, there could. Okay. Oh, we are interested only in one assignment. If there is a graph, if we find one particular assignment of edge weights and colors, such that some dimension is achievable, then the best possible such thing is the.
What generality classes of graphs plus such at least one such color assignment?
Oh, so we can consider the simple color assignment. Take a graph with even vertices so that the perfect matching exists, and then color the entire graph with the same color. So if this graph has a perfect matching, you can assign the weights as we defined here. Take all the perfect match. So they add up to 1. So any graph would have at least 2 if there is a perfect.
So suppose I only have a graph with a single color.
Yeah.
Is it clear that you can always have edge weight assignments so that the total sum is 1?
Yeah. So what we'll do is if there is no perfect matching, we can't do anything. If there is a perfect matching, we'll count the total number of perfect matchings, and we need to add all these contributions, right? So what we'll do is we'll make sure each of these contribution is, let's say there are 10 perfect matchings. We want to make sure each of these perfect matchings sum up to 1 by 10. So, contribute 1 by 10 to the total thing. So if you say, let's say this graph has n by 2 edges, we need to multiply n by 2 edge weights to get 1 by 10, right?
By 2 edges.
So let's say the graph has n vertices.
N vertices.
So there are n by 2 edges in a perfect matching.
Yes.
So you need to multiply n by 2 edge weights to get the final 1 by 10. Now what I'm doing is assigning 1 by 10 whole power 2 by n to everything, so that when you multiply, they'll just sum up to 1 by 10. That way you can extend it to multiple colors when such a thing. So we call this thing as the unweighted matching index, when all the perfect matchings are perfectly monochromatic and we don't have to worry about the edge weights. This corresponds to the case when there is no destructive interference. So by definition, since we are allowing only a smaller space for the no destructive interference case, mu bar of g, the weighted case, is at least the unweighted case when there is no destructive. No, we are interested in all graphs. Yeah, with the coloring which is perfectly monochromatic, which I defined. Every graph has such a coloring. We just want to find such assignment which is perfectly monochromatic and maximize to get the best matching index.
Will we see colorings where equal edge weights in the game?
Yeah. Yeah.
Not just that you always have to be.
They can be unequal. So when you want to cancel out things to, so the condition for a perfectly monochromatic in the weighted sense was that the non-monochromatic vertex colorings should sum up to 0, right? So there you need to somehow give some positive weights, some negative weights, or complex weights to give them 0.
I understand. I mean, edges with the same colors.
Even for edges with the same colors, we can set different amplitudes. Yeah, that's in. Yeah. Yeah. So there is a theorem due to Bogdanov, which says that if a graph is not isomorphic to K4, this unweighted matching index is at most 2, and when the graph is isomorphic to K4, the unweighted matching index is 3. And this is a simple result. I'll prove in a while. So based on this classification, since we know that if a graph has a perfect matching, its weighted matching index is at least 1, unweighted matching index. And if the graph does not have a perfect matching, its unweighted matching index is 0. We can classify all graphs into 4 types. So it's type 0 graph, type 1 graph, type 2, type 3 graph, based on the value of this unweighted matching index, as this is bounded by 3. So type 0 graphs are the graphs for which whatever assignment of colors and weights you assign, they cannot achieve a matching index 1 or more, or they can't achieve a high dimensional ZZ state. So when there is no perfect matching is the only case when this is possible. And for such a case, since there is no perfect matching, even the weighted matching index will be 0. And the other simple case is K4, where there is only one graph which is type 3, that is unweighted matching index is 3 due to theorem 2. All these are due to theorem 2. And for those, we can say that mu bar of unweighted matching index is 3, and we already proved that the weighted matching index is at most the minimum degree. So even this is 3. So we are seeing that they're both equal for this, but for type 1 and type 2 graphs, there are no known results. Actually, no. It's hard to, I'll have an example, I'll show why it doesn't happen. Okay, so we'll get to the main conjecture now. If G is not isomorphic to K4, earlier we proved that the weighted matching index is at most 2 for the unweighted case when it's not isomorphic to K4, and the unweighted matching index is 3 for K4. So this is a more generalization saying that same thing is satisfied even for the unweighted case. So even if you allow destructive interference, still the same thing works. But this is not proven. So Mario Krenn raised this conjecture in 2018. He announced some cash rewards for this. And we already saw that mu bar of G is at least mu of G, since we are only restricting the space over which we can look at the. And this is trivial for type 0 and type 3 graphs that they're equal. So this conjecture follows. So we want to know if a more general question that whether you allow destructive interference matter at all. Like we'll take a graph, whether you give only positive weights or a mix of all things, will these matching indexes, both weighted and unweighted, will be equal all the time? That's a natural thing to ask. That is, does having destructive interference help at all? So this is our theorem. We say that if the unweighted matching index is not 1, they're all equal. So for type 0 and type 3, it was trivial. So we prove that for type 2 graphs, both of them are equal. And there are graphs for which this does not hold when mu of G equal to 1.
What is mu bar of G?
2. Yeah. So since it is 2, we can't get a counter example to this conjecture. So in the view of result, now this conjecture is open only for type 1 graph, since this particular example have weighted matching index only 2. So now we'll prove Bogdanov's theorem, which was that unweighted matching index is bounded. Before we get to that, we'll look at a simple concept called matching covered graph. So take any graph, an edge can be part of some perfect matching, and there are edges which are not part of any perfect matchings. So what we do is we discard all those edges which are not part of any perfect matchings. Then given a graph, you can just remove those edges and you can get a matching covered graph, since each edge is covered by some perfect match. Okay. Now in the unweighted sense, we'll see what the perfectly monochromatic graph is. Yeah. So in this particular graph, there are 2 colors and both of them are monochromatic, both the perfect matchings. So in the unweighted sense, all the perfect matchings are monochromatic, and therefore this graph is perfectly monochromatic and unweighted. So this is the example you asked for, like one example for 6 vertices, where the simple things why it doesn't seem to work. There are 4 perfect matchings. Initially, I constructed green things here and red edges here, and I added some blue edges. Now there is a red perfect matching, green perfect matching, and a blue perfect matching. But this would also imply that there is a green, blue, and red perfect matching. So this is not a perfectly monochromatic graph. So it doesn't go to the space where we are considering to maximize the dimension so that we can get a higher matching index. So in this graph, there are three matchings which are monochromatic, and there is a matching which is not monochromatic. So this is not even in the solution space we are considering. We are considering the graphs only for which we can give a color assignment such that all the perfect matchings are monochromatic. Since this is not even in that space, we can't do this. So whenever we try to use more colors and try to get a higher dimensional Z state, this is a problem we'll always run into. We'll get a non-monochromatic perfect matching in there. That is what we used to prove the Bogdanov result now. That is, if graph is not isomorphic to K4, the unweighted matching index is at most 2, and weighted matching index is less than or equal to 3. Unweighted matching index is equal to 3 for K4. There's a typo there. Yeah, I started at 11, 10. I'll do it at 12. So proof idea is simple. We'll assume that there is a graph which is not K4, has a perfectly monochromatic graph with 3 colors, say red, blue, and green, and we'll prove a contradiction. So first, there's a simple fact that take any 2 perfect matchings and consider their union. It should be a disjoint union of cycles, because when you add up all the edges, each thing gets a maximum degree of 2. It's either a disjoint cycle or the edges overlap and you get an isolated edge. So we know that since we are considering there are 3 colors which is the perfect matching, pick red and green first, and their disjoint union will be some union of cycles. Now these cycles will have alternating colors. It's simple. So once you do this, you can pick all red edges from one cycle, and from the remaining cycles you can just pick the green edges. So this doesn't work. So there can't be a disjoint union of cycles. The only way this can be fixed is that the entire union is just a Hamiltonian cycle in which all edges have. So if you take all, I'll first take all the red perfect matching.
No, I got that. Now you in one cycle you switched.
Yeah, in one cycle I'll pick red, and in all other cycles I'll pick green.
Yes.
Now I have a non-monochromatic perfect matching. But all the perfect matching should be monochromatic, right? Right.
So
this is the unweighted case. I'm proving Bogdanov's result. So that case it doesn't work. Therefore, any 2 perfect matchings union should be a Hamiltonian cycle. Now, once we have the Hamiltonian cycle, we'll restrict how we know that there is a blue perfect matching in this too. We'll restrict how blue edges can be and get into some contradiction. So let's first consider the case where the blue edge goes from an odd vertex to odd vertex or even vertex. So let's say it partitions this graph into 2 even parts. So here on one side there are 4 vertices, and on the other side too there are 4 vertices. We say that such a thing is not possible. Let's say such a thing is possible. Then since both sides are even, you can pick a perfect matching from the top and perfect matching from the bottom. And therefore you'll get a new perfect matching in which the blue edge is also present, and there are other green and red edges too. So now we know that all blue edges should split this Hamiltonian cycle into 2 odd parts. Now let's assume that all these blue edges from perfect matchings are splitting this Hamiltonian cycle into 2 odd parts. So among all such edges, let's say in the earlier example, the edge was splitting it into 4 and 4. Let's say an edge splits the Hamiltonian cycle into 3 and 5. We call the smaller side, that is 3, to have the minimum partition weight. It is partitioning into 2 parts, and out of 3 and 5, we'll pick the minimum. Now, once among all the blue edges which are part of a perfect matching, we'll pick the edge with the minimum partition weight. So we know that there'll be at least 5 blue edges in this case, and each of them has a partition weight, and we'll pick the blue edge with the minimum partition weight. In this case, it's 3 for both of them. So let's pick one of those. Once you have this 3 partition, consider all these vertices here on this side, these three vertices, and pick its neighbor. We know that this neighbor can't go to one of these vertices. Let's say if it goes, then you are getting an edge with a smaller partition number. So I'm fixing the edge 1, 5, this one. Okay. There is an edge here, right?
Yes.
Almost horizontal.
Yes.
It's splitting it into two parts, 3 and 5.
Yes.
Now I'll take that split, pick the smaller section, 3, and this is the edge with, among, there are multiple edges, among all of them, this is the edge with minimum partition number. Now I'll pick the vertex which is adjacent to this vertex. So there is an edge between 1 and 5, right? Almost horizontal. Then I'll pick the adjacent vertex here. This vertex, let's say it's having an edge on the same side, on the smaller side. Then you are getting a new edge which has a smaller partition number, right? Because these two are not crossing each other.
It's having a blue edge, you mean? It's having a blue edge on this one.
Yeah, it has a blue edge.
Then that's a problem.
Yeah.
Yeah, that's a problem.
Huh. Therefore, we know that they should cross the adjacent edges starting from the adjacent vertices. And since both of them are odd, as we proved earlier, it will split this graph into three even parts. So this part is even, this part is even, and this part is even. Again, you have a new perfect matching. And therefore, we are getting a non-monochromatic perfect matching again. And we can see that this doesn't work for K4 because in K4, all these three parts disappear. That's why there you could get a matching index 3. So now we'll get to our result. That is, if mu of g is not equal to 1 for type 2 graphs, type 0 and 3 are trivial. Mu bar of g is mu of g. And we'll also give an example where mu of g is 1 and mu bar of g is 2. Okay. First, we'll give an example for type 1 graph where this happens. And the proof idea for the remaining is that we prove that if there is a certain gadget in a graph, then its weighted matching index is 2. And we then give a structural characterization of all type 2 graphs and show that it has either a 2-degree vertex or a gadget we just said. If there is a 2-degree vertex, we know that the matching index is at most 2, as we proved that it's minimum degree bound. We'll first start with the example. So this is an example where this is a type 1 graph. We'll prove that later. We want to prove that this particular thing has weighted matching index at least 2. It's exactly 2 because again the minimum degree argument. So it's just enough to prove a assignment where the dimension reaches 2. Okay, so in this there are 4 perfect matchings. And let's look at first type of perfect matchings where the edge 2, 3 is present. If the edge 2, 3 is present, you have a clique 1, 0, 5, 4. And this clique can give 3 different types of perfect matchings, and these correspond to 3 different perfect matchings. And the third type of the other perfect matching is when 2, 3 is not present. If 2, 3 is not present, 1, 2 must be present, 3, 4 must be present, and 0, 5 must be present. That's the fourth match. So these are all the perfect matchings. Let's consider the monochromatic ones first. So all the edge weights are +1 here, except this, where this is -1. In the monochromatic case, all of these, there are just one possible perfect matchings, and they're just 1. For the non-monochromatic case, there is only one possibility, which correspond to 2 perfect matchings. That is, 2 and 3 get the color green, and 1, 0, 4, 5 get the color red. And since these weights are +1 and +1, they add up to 1. These are -1 and +1, they add up to 0. So this is a perfectly monochromatic graph. There are 2 non-monochromatic vertex colorings. So this matching index is 2. I'll show it in a while. Okay, now we want to prove that this unweighted uncolored graph is type 1. That is, its unweighted matching index is 1. So let's pick any edge. Let's say we pick 2, 3. And let's say without loss of generality, it has the color red in the final color assignment. Now we know that the entire clique 1, 0, 5, 4 was having a perfect matching with the edge 2, 3. And since all the perfect matching should be monochromatic, all of these should get the color red in whatever assignment for type 1 graphs you give. So we are interested in an assignment of colors to this graph in the unweighted sense, so that the final graph has all perfect matchings which are monochromatic. That is what we define the unweighted matching index to. Let's say without loss of generality, 2, 3 is red. We'll start with this. Now we so consider the perfect matching 2, 3, 1, 0, 5, 4. This should be monochromatic because all perfect matchings are monochromatic in this set. So therefore 1, 0 and 5, 4 should be red. Again 1, 4 and 0, 5 should be red, and the entire clique should get red. And now pick the perfect matching 0, 5, 1, 2 and 3, 4. Again, they all should be red. So this entire graph should be red, and it is a type 1 graph. Unweighted matching index is 1. And we proved that the weighted matching index is 2. This was a simple example. Now we are interested in looking at the weighted matching index of type 2 graphs. We'll first see what's happening to prove the bounds on weighted matching index by others. So one line of research attempts the problem by treating weights as, so they fix a color assignment. There are multiple possible weights possible over this color assignment, and they treat all these weights as variables. And we have mu power n equations. That is, we know that all monochromatic vertex colorings should sum up to 1, and all non-monochromatic vertex colorings should sum up to 0. So there are mu monochromatic vertex colorings. All of them would sum up to 1. So we have mu equations there. And for the non-monochromatic coloring, since there are n vertices and each vertex can get mu colors, there are mu power n total possible colorings, out of which mu are already taken.
By mu, you mean mu bar?
Yeah, mu bar, sorry. And mu bar of g power n equations. And they try to. Yeah, mu bar is number of colors in the weighted case. So once they get this sort of assignment, they use some optimizations on this, and they use SAT solvers to and some other techniques to solve these equations. And using those, they proved that weighted matching index was bounded for small graphs. That is, for 6 vertex graphs, they proved that the weighted matching index is less than or equal to 2. For an 8 vertex, for any 8 vertex graph, they proved that vertex matching, the weighted matching index is at most 4. But they couldn't get any counter example for example. So we take a completely different route. We don't worry about these equations. We just use the structure of the graph. As we said, we'll find a gadget and we'll prove that the type 2 graphs have that gadget. So this is the gadget you're asking for. If the graph has the following induced subgraph with 3 and 4 having degree exactly 3. So that is 3 and 4 have no other edges. There are some n vertices in this graph, and pick 1, 2, 3, 4. Now 3, 4 have degree 3, so there are no other edges, and the remaining graph comes out of 1 and 2. If there is this particular graph, we prove that the weighted matching index is at most 2. Then we show that this gadget must be present if there is no 2-degree vertex in type 2 graphs. Let's see why this gadget works. So towards a contradiction, we assume that the graph contains such a gadget and has matching index at least 3. So we can pick 3 colors, red, blue, and green. And I'll go to the vertex 3. We know that the vertex 3 should have a red edge, green edge, and blue edge. Because otherwise, there won't be a, let's say if there is no red edge, then there won't be a red perfect matching, which covers 3. So now if I go to the 4 vertex, even there should be all 3 edges. This was without loss of generality. So there are 2 possible ways to fill this. One is doing the red this way, and other is this way. The first is can be easily ruled out, because if we give this particular coloring, then any perfect matching which is red in color, monochromatic, 3 should have 2, 3 2 edge should be there. But when you go to 4, it should also have 4 2, but 2 is already covered. So that's not possible. All the perfect matching you take, either 2 3 1 4 is present, or 2 4 1 3 is present, or none of these are present in this.
So do you allow 1 2 to be an edge or not?
No, we don't allow.
So the rest of the graph comes from 1 and 2.
Yeah, 1 and 2 are disconnected. So now we look at the other case. So let A be the set of vertices excluding 1 2 3 4. And for the second possible coloring, which is the we'll first look at the small part. So take any green perfect matching. Then this green perfect matching must have the edge 1, 3. And it must also have the edge 2, 4. So when you take a product of all the edge weights in the perfect matching, these two always happen to be the factor of that product. So one thing you can do is you can just take these factor common when you're adding these perfect matchings, and the remaining A vertices other than 1, 2, 3, 4, they just have the some additive terms with them. And we know that this product, weight of 1, 3, weight of 2, 4, and weight of entire A vertices colored green is 1, because this is the monochromatic vertex color. So similarly, if you take the red monochromatic vertex coloring, it
this is an induced subgraph.
Yeah.
This is a disconnected one.
No, so the entire graph comes out of 2 and 1. If it's disconnect,
Only 2 and 1.
Yeah.
3 and 4 don't have.
3 and 4 have nothing. So another thing, if there are disconnected components, we can't do anything. Sorry, we have a result, but we'll. So similarly for red, you have weight of 2, 3 into weight of 1, 4 is.
It's connected, right? The graph is connected.
Yeah. For disconnected case too, we can take the individual components and do it. We'll skip. Yeah, now we are taking them. So now take the coloring in which 1, 2, 3, 4 gets the color green, and the remaining A vertices get the color red. So I'm taking the coloring in which 1, 3 is green, 1 vertex and 3 vertex. 2 vertex and 4 vertex are also green, and the remaining A vertices are red. This is possible because we know that there is a red perfect matching in which 2, 3 and 1, 4 are there. So we'll just pick all of them. Now, the weight of this particular non-monochromatic vertex coloring is nothing but weight of 2, 3. Again, this edge must be there in all such colorings, because 3 gets the color red only when 2, 3 is present, and 1, 4 must be present. So the weight of such a coloring is nothing but weight of 1, 3 into weight of 2, 4 into weight of A being red completely.
The weight of the red, you said green.
So first we proved that weight of entire green perfect matching is 1. Then entire red is 1. Now I'm saying, so we know that these parts are non-zero.
Yeah.
Then we'll get to the coloring where 1, 2, 3, 4 are green, and the remaining part is red. This is a non-monochromatic vertex coloring. Now if you go to the vertex 3, this is green only when the edge 1, 3 is present. And if you go to the vertex 4, this is green only when 4, 2 is present. So in all the perfect matchings corresponding to such a coloring, these two should be there. So again, there will be a product. And the remaining term will be same, weight of A being colored red. But we know all these terms are non-zero, so it's non-zero. But we know that non-monochromatic vertex coloring must have 0, so it's a contradiction. So the gadget can't be there. So we'll get to the structure of, we'll see what the structure of type 2 graphs is. I'll not do the proof of this. So we earlier saw that if it's a type 2 graph, there is a perfectly monochromatic colored graph with 2 colors, pick, let's say red and blue or something. We consider such a colored graph and we see the structure over such a colored graph. So let's say if they have 2 perfect matchings, they should form a Hamiltonian cycle. This is because we saw the argument earlier that it will become a disjoint union of cycles. Now take such a Hamiltonian cycle and order the vertices in cyclic order. So I put them 0, 1, 2, 3, 4, so on. Now we prove that any type 2 graph, that is, if the best possible dimension a graph can achieve is 2, then the graph should have the following structure. So I'll put it in the uncolored sense so that we get a better idea. So we had the Hamiltonian cycle, which we picked earlier, and every other edge other than the non-Hamiltonian cycle edge, they should form drums. So each of this drum looks the following way. You pick 2 edges and the 2 Hamiltonian edges, let's say 4, 5, and 6, 7, and the edges should be drawn in between them so that they cross. So it's a cycle, but which is alternating. So I'll get to this figure. You first pick any 2 edges of the same color on the Hamiltonian cycle, and then you cross them. These are the only possible structures for type 2 graphs. I'm not doing the proof now. And if you can see that this drum is not just a cycle, I plus 1, j minus 1. So all cycle edges, there are some properties for this graph. That is, if an edge is not Hamiltonian, then it must be part of a drum. I mean, the Hamiltonian cycle with respect to this ordering of 0, 1, 2, 3. All the other edges should be part of one drum with respect to this cycle. And these drums don't intersect. So they're all. So this, once we remove the colors, it will look like this. So I'll just do this small proof and we'll end the talk here. So in this particular graph, we want to prove that it either has a 2-degree vertex or there is a gadget we just proved that which shouldn't be there if mu bar of these. So I'll pick a drum such that all vertices on one of its sides have degree 2. There, in this particular case, there are no such things, but okay, I want to prove that such a drum exists. First, similar to the minimum partition weight of an edge, even a drum splits the graph into 2 parts. Now I'll pick a drum with such a minimum partition weight out of all possible drums. And we know that drums won't intersect. So for this statement, there exist drums such that all vertices on one of its sides have degree 2. Let's say if there are no such edges, no such vertices, that is, this weight is 0. Then the gadget should appear in the graph, because if there were other vertices, you would get a line, series of paths like this. Since there is no such vertex with 2 degrees, it's only possible when 3, 4 are just connected. And for the non-zero case, that is, if there are vertices, we want to prove that, assuming that we want to prove a stronger condition that all vertices on the minimum partition side have degree 2. Let's say that is not the case. Then there exists some vertex which has degree at least 3. By definition, since it's degree 3, there is a non-Hamiltonian edge there, and it should be part of a drum. And we proved that these drums are non-intersecting. So you get a drum with a smaller minimum partition weight, which is a contradiction again. Therefore, there will be a drum with smaller partition weight, and all its vertices on one side will have degree 2. And with this claim, when there is some vertex, we are done of this satisfying this property. If there is no vertex, we know there will be this gadget. So we are done. So for all type, if a graph has the weighted matching index 2, then the unweighted matching index is 2 for a graph, then its weighted matching index should also be 2. So simple thing we ask is I'll skip the proof and the idea. So next thing is, can we bound for type 1 graphs? We saw that we bounded by minimum degree, and we know that the edge connectivity is at most the minimum degree. So we improve that minimum degree bound to edge connectivity. I'll not prove that. And the bicolored edges is what complicates this problem to get better bounds. So we relax that condition and get several other results based on maximum degree and vertex connectivity. And the final, and for the case when there are no bicolored edges, Tiveria and Leata et al. Proved that this weighted matching index is at most 2 if the graph has 6 vertices. For that, we give a simple combinatorial proof. They proved it using SAT solvers, solving all the system of equations. The final thing is, we looked at graphs only which doesn't have multi-edges. Now it's okay to allow multi-edges in the graph, and that complicates things a lot. Let's say you pick a small 2-vertex graph. You can just add all edges with multi-edges of different colors, and that gives you a matching index of infinite. But after 2, for 2, you get the experiment is not suitable, or is it? I don't know about that, but we are interested even to find an example for which matching index is at least 3, even in multi-edge setting. And it's very hard to prove it even for graphs with 4 vertices combinatorially. So take a K4, you have each edge. Let's say you want to prove the matching index is less than or equal to 3. Okay, equal to 3. You take any edge. There can be how many possible edges if there are 3 colors. This vertex can get 3 colors, and this vertex can get 3 colors. So there are 9 different edges possible, multi-edges. If there are the same color, you just add the weights. And so there are 9 into 6 edges, and there are 3 power 4 equations that all vertex colorings are 0. And combinatorially, like unless you find something very clever, which we couldn't, you can't solve this. And so it's proved using SAT solvers that for K4 this works. It's 3, but it's very interesting to see if someone can, if one of you can solve this. Thank you.
Particularly would help when you're solving a particular case, but how do you do it for all classes?
So you can consider all the colorings and first fix a coloring. No, so take a graph, you color. There are multiple colored graphs for this. And for any colored graph, there are multiple possible weight assignments. Now, once you have these weight assignments, you can write down all the possible equations that monochromatic vertex colorings have weight 1 and non-monochromatic vertex colorings have weight 0. So let's say if there are mu bar colors, you'll have mu bar of g power n many equations. And the weights are, since there are e edges, you know that there are e variables because each edge weight is a variable. Yeah, and we'll check it over all possible colorings. This is the brute forcing. They use some clever techniques to reduce this and like get a faster thing on a SAT solver. So you are saying all of them are 4. So then we have the gadget, right? They can be 4. All of them can not leave any 2-degree vertex. But in that case, any of them will give the gadget we want. Were you asking about the definition of the drum? What? Okay, so to get the definition of the drum, once you have this Hamiltonian cycle with the alternating color edges on the top, you pick any 2 red edges, and let's say I pick 0, 13, 3, 4. You can't have an edge from 0 to 3 and 4 to 13. You can only put an edge from 0 to 4 and 3 to 13. That is, they should cross each other when you just connect them. That forms a drum. And none of these drums cross each other, like they're separated. So there can't. Yeah, if there is a separation, then that would imply that there is a 2-degree vertex. Then we are done. So we are in, when the case there is no separation, we'll end up having a gadget. Multi-edge case?
Half edges.
Yeah, all these proof work for multi-edge, half edges. And our proof can be extended to multi-edge too for type 2 graph. Modulo that K4 is correct. We don't have a combinatorial proof for K4, but we know that it's correct from SAT.
You get some money from this guy?
Yeah. So the main question is still open. And there is a boundary on the main question too. If you find a counter example or prove it to be correct, the conjecture. Yeah, the question is to find the counter example so that you can create a high dimensional GZ state which is useful in many applications.
For example, to what?
So if you find a graph with a high matching index, the conjecture was that all graphs have matching index less than or equal to 3. Yeah, so if you find a counter example to that, you can end up creating a high dimensional GZ.
But the belief is that it is correct.
Not really. So it's by a quantum physicist.
No, I know. So what?
So they tested multiple experiments and they couldn't achieve any setup with.
So what? They have issues. I mean, if it were easy, then we could have already done something.
Yeah.
Right, and they are not getting. That's why they conjecture. There is no reason why they don't know how certain things work and the graphs are being conjectured. Right.
But he is offering money. So
Because he is very interested in that.
So again, all the seat as a question.
do some experiment.
Yeah.